In this video, we're looking at the product rule, and it's a way to differentiate products, or in other words, it's a way to differentiate things that are times together. There is the formal full definition up here, but I like this condensed definition that gets rid of all the bracket X bits. So that's the one we're going to be using. Okay, so let's have a look at a few examples. We have this first one, which is to differentiate this function. Now, you definitely could, if you wanted, just expand everything out and then differentiate it bit by bit. But using the product rule, we're going to make our life a little bit easier. What you always do with the product rule is you figure out what u and v are. And in this case, this first bit is going to be u, and this second bit is going to be v. And the kind of functions we differentiate using the product rule look like u times v, which this one is. I'm going to write it over here. U equals 2x, and v equals x squared plus 1. Now I always write what my u dash and v dash are, and that's basically the derivative of u and the derivative of v. So that's 2 and 2x. Now the product rule basically tells you f dash of x is going to be u dash v plus u v dash, and that comes directly from that formula up here. And now we just plug them in. So u dash is 2, and v is x squared plus 1, plus now u is 2x, and v dash is, well, 2x. Often you're fine just leaving it like that, but if you want to simplify it, plus 4x squared. So I got 4 from the 2 times 2, and then the x squared from the x's times together. If you really want to get fancy, you can expand that out and then collect like terms. But usually with product rule questions, you're fine just leaving it at this point. Okay, next one we're going to do is differentiate this function here. So again, you could have just FOILed this out rather than using the product rule and done it term by term, but the product rule speeds it up a little bit. Some things we'll find later on down the track will be impossible to differentiate without the product rule, so it's really important we know this. X cubed plus 5, and then 2x plus 3 are our u and our v's. U dash is going to be 3x squared, and v dash is going to be 2. So the product rule tells us the derivative is u dash v plus uv dash. So that's 3x squared times 2x plus 3 plus x cubed plus 5. And then I'm going to times it by v dash, which is 2. I'm just going to put that out the front there. Done. Again, you could simplify it, but you're usually not required to unless it's a multi-part question. Here we have u and v. So u is going to be x take 4, and v I'll just write it as x to the power of a half, because that'll help us differentiate it. U dash equals 1, v dash equals half x to the minus a half. Okay, dy dx is going to be u dash v plus uv dash, which is 1 times x to the half plus x take 4 times a half x to the minus a half. If you want to simplify that a bit more, you've got root x plus x take 4 over 2 root x, if you want to have that simpler. Great. Now I want to show you this one. We do know what the derivative of this is. We know that it's 2x is the answer we're expecting. But I want to show you that this is possible using the product rule. So if I were to write it as y equals, well, x squared is a fancy way of writing x times x, then you would have u equals x and v equals x. U dash equals 1, v dash equals 1. So the derivative is going to be u dash v plus uv dash, which is 1 times x plus x times 1. Or in other words, that's x plus x, or 2x. Isn't that wonderful? So the product rule is consistent with the rules we already know, which is great, because if that wasn't the case, we'd be in big, big trouble. So that's a good idea. When you find out a new rule like this, it's good to try it on something you already know the answer to, like this, and see if the product rule gives you the answer you expect. Really important.